Hello guys, so welcome to the second part of the four-part series on namespaces. So here we are going to dive deep into the Linux PID namespace. We will see how Docker and container makes use of this fundamental Linux feature to isolate processes and provide processes to containers or a container in a pod. In the last episode, we saw how UTS namespaces give containers their own hostname. Today, we are going one level deeper into process isolation because containers are just Linux processes, but they don't see all processes. So, what is a PID namespace? A PID namespace gives processes their own private view of process IDs. Inside a container, PID1 is not the host in its system, it's your application. So, now the question comes, why PID1 matters? Why PID1 is special? So PID1 receives signals like sigterm, sigint, responsible for reaping zombie processes. So bad PID1 is equal to a broken container. This is why badly written containers fail during shutdown. Your app becomes PID1, whether you planned for it or not. So now let's see how the processes are on a host machine. For example, a OS where there is maybe a Ubuntu OS. Let's see how the processes are on the host machine. So we'll use the ps command, ps-ef -head we'll do. So it gives you all the processes that are there on the host. And this one, the PID1 is the one that is a systemd or a init process that is a true PID1 for the host machines. It's a host init system. It can see many processes. In hundreds also you can see. So now we will see how Docker makes use of the PID namespace feature. So let's go about spinning up a simple Docker container with busybox image. So we will do a Docker. So we have a Docker container running. If you can see, yeah, we have a Docker container running. So let's exec into that. So we are into the Docker container now. Let's see how the PS for this works. So as you can see, there is only one PID namespace for SH. So let's exit out and also do a inspect on the container and see and get the PID of it. So we will do a Docker inspect. We will do a Docker inspect and get the PID. So we have got the PID as 24671. Now let's see if this PID is there on the host machine. We are on the host machine now. So you can see there is this namespace and the PID that is there. You can see SH and you can see it on the host. So inside the container, the shell we saw is PID1. On the host, it has a different PID, completely different. So same process, two different views. So that's PID namespaces that Docker leverages. So Docker automates all the things that we did using unshare. Now we will see how Kubernetes also leverages the same foundation of PID namespace. So we will run a pod and then exec into that and see how the process is there for a particular container in the pod. So let's do that. So we have a simple pod here. So this is the pod definition that we have. We are using a simple busybox image and just doing a sleep, and then we will exec into this and see the process or a PID. So let's apply that. So the pod is up. So now let's exec into that and let's do a PS here. So as you can see, you have a PID1 for the sleep that we used in the pod definition, right? So it has its own PID. So inside the pod, the container again sees itself as PID1. So Kubernetes relies on the same Linux PID namespace feature, nothing magical. So we saw in Kubernetes when a pod had container spun up, it got its own process ID. But Kubernetes also provides a feature wherein pods and containers within them can see each other's PID namespace, they can share them, and they can see and signal each other's processes. So this becomes possible when we add in this spec, that is share process namespace equals true. So this makes sure that containers within pods can see each other's processes. So we will demo two behaviors, one wherein the shared namespace process equals true, wherein the process will be shared among containers in a pod, and one without sharing the process within the two pods. So by default, Kubernetes gives each container its own private process ID namespace. So every container in a pod gets its own PID namespace, even when running in the same pod. Their processes are invisible to each other. So one pod cannot see the process ID of other container in a pod. So for example, a container A won't be able to see the process ID of container B. And same goes for container B won't be able to see the process ID of container A. So that's a default behavior. So first we will create a pod with two containers without using the share process namespace feature, wherein the containers within the pod won't be sharing their process namespace between them. So let's go about doing that. So just let's apply this. So our pod is created now. So now let's exec into two containers and see how the process and process IDs within those containers are. So if you can see, it has its own process ID. Let's get out of this and see the other container, that is a sidecar container that we have named it. So here also it has its own PID, and they don't have any information about the PIDs. For example, sidecar won't be having information about the PID of app, and app won't be having information about the PID of sidecar. So if you notice something interesting here, both containers think they are PID1, but they cannot see each other. That's because by default, Kubernetes gives each container its own PID namespace, even inside the same pod. Now let's go about and change the default behavior that Kubernetes offer and use the share process namespace is equal to true. What this does is this tells Kubernetes to place all containers in the pod into a single shared PID namespace. So let's apply this manifest. We will say kubectl apply -f and pod share. So our pod is up now. Now let's exec into the pod and see how the process ID is for the app container and the sidecar container. So let's see first the app container. So if we can see, you can see the process IDs. There are two process IDs with sleep, 7 and 13. Let's do the same for the sidecar container. So as you can see, same. These are visible from both the containers. So now let's demo one more part, that is how can we control from one container the other container's process. So let's do one thing. Let's create a sleep in the app container. So let's exec into that. So we have exec into that. So let's say sleep 999 and put it in 1%. So if you do a PS, you have a process ID for this sleep that we just created. Now let's exec into the sidecar container. Let's see a PS from here also, and let's kill the process ID that is 39 for the sleep. So as you can see, the sleep that we created in the app container is killed. So the fact that one container can see and signal a process started in another container proves that they share the same PID namespace. So now the question arises, why to share the PID namespace within the containers? So there are many real world use cases. For example, to debug sidecars. For example, using a sidecar to debug the main container, or a monitoring agent, wherein a lightweight agent runs in a sidecar to monitor the processes of the main application. Log collectors. A sidecar can tail log files or manage log related processes. Advanced health checks. Implement custom process level health checks from a sidecar that can inspect the application state more deeply than a standard liveness probe. So these are the real world use cases wherein sharing the PID namespace among the containers becomes useful. So Kubernetes doesn't invent these concepts. It provides a powerful abstraction over core Linux internal features. Understanding the mapping is key to mastery. So the core takeaway and what we learned from this namespace thing is PID namespaces explain why containers feel isolated. The shared PID namespace that Kubernetes has to offer explain why pods feel like one machine. So why would you enable shared process namespace? If you get asked this in some interview, you need to answer it like this. To allow containers within the same pod, like a sidecar, to inspect, monitor, or signal the main container's processes. It's essential for advanced debugging and monitoring patterns. So, PID namespaces answer a simple but powerful question. Why does every container think it's the only process in the world? Because Linux made it so. So, if you see the mapping in this table, the Linux kernel feature that Docker and Kubernetes both use. So, when we created a namespace using unshare, the same was done by Docker. Automation was done by Docker of using the unshare command and creating a PID namespace. The same was done in Kubernetes, wherein a pod got its own PID namespace by default. Then we also saw how the process inside a container or a container in a pod got its own PID. That might be through CMD or entry point in Docker that we specify in the Docker file. So these becomes PID1, wherein the application itself becomes the PID1. Same goes for the container that spins up inside a pod. We also show the power of shared PID namespaces, wherein we used in Kubernetes the feature called shared process namespace, wherein the containers within the pod were able to share the PID namespace. So in next episode, we move from process isolation to network isolation and explain how every container gets its own IP address. Stay tuned.